All right, so let's start with the warm-up. So I give you a solution, not the general solution, but a solution to two different second-order homogeneous problems, and learn what we used in the last video to find the general solution. All right. So I want to explain this somewhat, more in depth, but also I don't want to write a ton. So I am going to say that capital F of y is y double prime plus 2y prime minus 8y. All right, so you didn't necessarily need to do this but to explain it, but I want to give a sort of in-depth explanation. So, okay, so we know then that f of 1 minus 4t over 32 gives us t, and so f of negative 4 times that needs to give us negative 4t. Similarly, we know how to get 5 times e to the t. So to get 10, we know that f of 2 et should give us 10 et. Okay, so in particular, what this tells us is that I can take one solution to be 2 et minus 4. I'll just go ahead and simplify this up here. 4 over 32 is the same thing as 1/8 minus, so 4t minus 1 over 8. And so this is one solution, one particular solution, but we're not done. We need to find the general solution. That said, we just need to solve the complementary equation. It's pretty straightforward, so I won't try. I'll just tell you that your complementary solution is going to be c1 e to the negative 4t plus c2 e to the 2t. And so what we get is our general solution is the sum of these two things. All right. So to give the briefest of summaries, what we learned last time, how to solve stuff that looks like this. Second order linear non-homogeneous equations. So step one is we're going to find the complementary solution. So that just means we go ahead and solve stuff like this. Most of the time we're just going to be dealing with stuff where we have constant coefficients. So let's just call that, YC. which we know has to look something like that. Step 2 is find one solution. Oh. Call that YP. This is our particular solution. And step 3 is just put it all together. Okay, so this step we sort of know how to do. In general, we're going to assume that these are constant coefficients, so you just looked at the characteristic equation. This step we haven't talked much about, and we're actually going to look at sort of 2 separate methods for solving these. And in this video, we're going to talk about the first one. So this first method is called the method of undetermined coefficients. And that's just a fancy name for semi-educated guessing. So let's look at our first example. So find the general solution to y double prime plus y equals 10 e to the 2t. And more specifically, let's just say, use the method of undetermined coefficients. Okay. So step 1, solve the complementary equation. And we should get that our fundamental set of solutions is cosine t sine t. All right, step 2. So of course, again, I'm not really showing step 1 on the exam. You're definitely going to need to show that. But okay, step 2. So step 2, we are going to just sort of guess for a form. So YP, we're just going to sort of assume that it looks like some number times e to the 2t. Okay, so why do we do this? Well, remember that if we take a derivative or a second derivative of e to the 2t, we just get something times e to the 2t. So that gives us like a pretty good, idea that as long as these coefficients here are constant, which they generally are going to be for this method, like we should be good and just be able to solve for A. We'll see later that doesn't always work, and we'll talk about how to get around it, but okay. So if this is yp, yp prime is 2a e to the 2t, and now we'll just plug this in. So we have and we want this to be equal to 10 e to the 2t. So we have 4a e to the 2t plus a e to the 2t equals 10 e to the 2t. Divide through by e to the 2t, which remember we can do for a lot of reasons. One reason is it's never 0, and we get 5a equals 10, and so a equals 2. That lets us know that our particular solution is 2 e to the 2t. All right, so step 3, we have a particular solution. We have a fundamental set of solutions. So the general solution is our particular solution plus c1 cosine of t plus c2 sine of t. All right. Let's do one more example, and then I will discuss sort of how we're going to get our guesses in general, at least our first initial guesses. All right. So again, not going to show it, but our complementary fundamental set of solutions to this problem is just going to be e to the 3t and t e to the 3t, because our characteristic equation is going to have a repeated root. Okay, so now we're going to take our particular solution, and it might be nice to just sort of start off with a t squared, and we know we can sort of get part of it, right? Because we have y here, so we could hopefully at least solve for a to make sure that this shows up. The problem is when we take derivatives, we're going to get 2a times t, and yp double prime will just be 2a. Okay, so if we go ahead and try to plug this in, right, we would have an a t squared here, and we would actually see that a would have to be 2, so that 2 times 9 is 18. But we're going to run into an issue right away, in that we're going to get something else that is not over here, but is on this side. So we would have a 2a here times 6, and that is not on that side. So to account for that, we're going to add a t term that is just going to cancel with the extra stuff that shows up when we take derivatives. And as you might guess, we're also going to need a constant term to cancel with some stuff as well. Okay, so going down, our derivative then is just going to be b and our second derivative is actually still just 2a. So now let's go ahead and plug all of these pieces in. So y, you don't have to show this step, I'm just doing it to make sure where everything's coming from. So this is just going to be 2a minus 6 yp prime 2at plus b, and then plus 9 times everything, at squared plus bt plus c. By this step, it's a good idea to show this step, but you definitely don't have to like rewrite the equation. Just making it sure where people can follow where every sort of term is coming from. All right, so the way we are going to proceed is as follows. We're just going to sort of collect all the like terms. So collect all the t squared terms, all the terms with just a t, and all the constant terms. And one thing that is really easy to do is to forget to distribute. So make sure you don't do that. So we're going to have 9a times t squared. We'll look at our t terms next. So we're going to have 9b and a negative 12a. And then for our constant terms, we're going to have 2a minus 6b plus 9c. All right, so now we're going to set up a system of equations that are necessarily going to need to be satisfied. So you could always just plug in values for different t values. It could be useful, but this ends up being like not necessarily the best approach, especially when you have more complicated guesses later on. So let's just sort of identify terms. So we have a t squared term and a t squared term here. So we have 9a t squared equals 18 t squared. We have t terms here, but no t terms over here. So, we can just sort of think we have, plus a 0t. And so we have 9b minus 12a t equals 0t. And similarly, we have constant terms, but there's no constant terms here. So 2a minus 6b plus 9c equals 0. And now I can just sort of divide through by the t because we need it to always be true, right? So we have 9a equals 18. 9b minus 12a equals 0. And 2a minus 6b plus 9c equals 0. So we can see then a has to be equal to 2. I can rewrite this equation then. I'll pull out a 3 first. 3b minus 4a equals 0. So 3b equals 4a, which is 8, and b equals 8/3. Okay, lastly down here, we'll plug everything else in. So 2 times 2 minus 6 times 8/3 plus 9c equals 0. So 4 minus 6 times 8/3, that'll cancel, giving us a 2/16 plus 9c equals 0. See, 9c equals 12. So c equals 4/3. Okay. Remember, just because we've solved for our things, we're not done yet. We still should put it back in here first in our particular solution. So let's remember what it was. A was the 2, and that was our t squared coefficient, so this is going to be 2t squared. B was 8/3, and that is our t coefficient. And we got plus c, which is 4/3. So still not done yet, right? This is just our particular solution, and our general solution is this plus the terms coming from our fundamental set of solutions. We had e to the 3t all right. So let's talk about the forms of our guesses. So there's nothing really, okay, well there's one trick that we'll talk about, but in general, forms of initial guesses. So there's one caveat to these, but we're going to look at some equation a y double prime plus by prime plus cy equals f of t. And what should our guesses look like? Well, I'm going to also say if so I'm not going to use this till later, but we're going to let p of t denote a polynomial of degree n, so up to t to the n. Okay. So again, we're talking about this f here. So if f of t is c e to the rt, right, then what we're going to want to do is our initial guess for our particular solution is just going to be a times e to the rt. So for instance, if we had something like y double prime plus 2y prime, plus 16y equals, 108 e to the negative 7t. Then our initial guess would be, just some constant a that we have to solve for times e to the negative 7t. If f of t is, let's say some number, let's call it k now, times cosine of at, or k times sine of at, then we're going to want to make sort of our initial guess is going to have plus a cosine of at, and then plus b sine of at. You're generally going to need both terms. Just a little shortcut. You can get away with using both terms really only if this b coefficient here is 0. If the b coefficient is 0, It turns out if you plug in, because the second derivative of cosine is again just in terms of cosines, you can sort of avoid the sine term. But in general, you're going to need both. So again, y double prime plus 2y prime plus 16y equals 10 cosine of 3t. Then our initial guess is a cosine of 3t plus b sine of 3t. Similarly, if f of t is some constant times e to the rt cosine of at, then we're going to have the same thing. You should have both cosine and sine terms. This one basically all the time, even if that middle term is 0. And again, okay, so if we have some polynomial, then our initial guess is going to be a polynomial of the exact same degree. Some coefficient a times to the n. Hopefully it won't, we're not probably going to give you anything more than like n being 3, but you do want to take it all the way down to the constant term. And lastly, if you have the same polynomial times e to the rt, our initial guess is going to be yp equals a t to the n e to the rt plus b t to the n minus 1 e to the rt, and so on. All the way down to the constant term. And when computing with stuff like this, it's really, really useful if you pull the e to the rt out, like when you're taking derivatives. Just sort of a tip. Because you then only have to do the product rule once. So pulling it out like that when you're taking derivatives can save you a ton of work. Yeah. Okay. So let's look at an example and see. So these guesses will sort of work almost all the time. I would say in practice, and maybe 40 to 50% of the time in this class, because we're going to obviously try to test you on the trickier ones. So right by here, right, our initial guess for our particular solution would be a e to the 4t. But let's look actually at what happens when we plug this in. So yp is 4a e to the 4t and yp double prime is 16a e to the 4t. And so if I try to plug this in, I did not give myself enough room. 16a e to the 4t minus 5 times 4a e to the 4t plus 4a e to the 4t. Right, and we want this to just be equal to e to the 4t. Well, we can pull that out, just divide through, and we get 16a minus 20a plus 4a equals 1. But if we simplify that, we get 0a equals 1, and we can't solve the equation. Okay, so here's what's going on here. If we look at the fundamental set of solutions, right, 5r squared minus 5r plus 4 equals 0, we can factor that as r minus 1 and r minus 4, and we get our fundamental set of solutions, e to the t and e to the 4t. Right? So this is our problem here. Our guess is actually part of the fundamental set of solutions. And really just, here's really just how we get around this. It's really the same thing that we do in repeated roots. So if your guess, or even part of your guess, shows up in your fundamental set of solutions, you just sort of modified guess and the rule is that you multiply by t until that doesn't happen. So in this case, if I multiply by t, I can see now that t e to the 4t is not part of my fundamental set of solutions, and so I am good. I can go ahead and proceed. So whenever this happens, it's kind of a double-edged sword. First of all, your derivatives are, of course, going to get more complicated because then you're going to have, possibly multiple product rules at every step. With that said, something nice is going to happen when we plug them in. So derivative of that, 4a to the 4t and 4h, so 8a e to the 4t. All right. So now look what happens when we plug this in. So we have 16at e to the 4t plus 8a e to the 4t, right? This is our y double prime. We have minus 5 4at e to the 4t plus a e to the 4t, and then just plus 4at e to the 4t. All right, so I'll distribute just so you can see exactly what's going to happen. Negative 20at e to the 4t minus 5a e to the 4t, then plus 4at e to the 4t. So if you've done everything right here, and I'm setting this equal to the wrong thing. This should still be equal to what we want it to be equal to this side, so just e to the 4t. All right, so we have a 16, a negative 20, and a positive 4. So that means all of these terms are going to cancel out. And we should expect this to happen because there's no t e to the 4t term on this side. So when you're doing this in practice, at least what I do is, I write out the derivatives. I maybe check mentally just real quick that it should work, but I can kind of just ignore all of these terms. They're all going to cancel out, and you're going to be left with a much simpler equation. So we have 8a e to the 4t minus 5a e to the 4t equals e to the 4t. Again, we'll divide through and we get 3a equals 1, so a equals 1/3. Our particular solution is 1/3 e to the 4t. And looking back up here at our fundamental set, we have our general solution is precisely this. Okay. So sort of our corrected guess is take your initial guess multiply by t until all terms of guess are not solutions to the complementary equation. All right, so I want to do some examples, but because, these can take a while to solve, I'm just going to sort of give the correct form of the guess. And we're going to do a bunch of these. All right. Give me 1 second. So for our first one, we have y double prime minus 5y prime plus 6y equals 10 e to the 4t. All right, so there's two things we need to look at, right? So we have our initial guess, which we know is a e to the 4t. We have, now before we continue though, before we know if this is a correct guess, we need to check our fundamental set of solutions. So again, I'm going to leave this up to you, but this one's pretty easy to factor. R squared minus 5r plus 6. We should get that we have e to the 2t and e to the 3t. So this is our initial, this is the correct guess. Continuing, we could have something like this. So here, our fundamental set of solutions, you're going to have a double root of 5, so e to the 5t and t e to the 5t. Our initial guess is yp. Note we have a t here, so and there's not actually going to be a problem. This isn't going to be a solution. So we have t a e to the 3t and then plus b e to the 3t. And that should work out for us. So continuing, if we look back, y double prime minus 5y prime plus 6y equals 7 e to the 3t. Well, we're going to have the same fundamental set of solutions as up here. Our initial guess is still a e to the 3t, but our corrected guess is a times t e to the 3t, because e to the 3t is in our fundamental set of solutions. Here our fundamental solutions is that, and our initial guess is, well, we have a t squared there, so we want a t squared plus b t plus c. None of those, note we would have a problem, let's say if this term was gone, because then a constant would be a solution. But because that's not the case, we don't have to worry about it. Going to write out the rest and then just go through them real quick. Okay, so our fundamental set of solutions is e to the negative 5t and e to the 7t. No problem with the cosine, so our final guess is a cosine of 3t plus b sine of 3t. Here, our fundamental set of solutions is e to the negative 3t and t e to the negative 3t. And this one's pretty important. So our initial guess would be something like this. But note, both of these terms belong to our solution. So to make sure that none of the terms belong to it, rather the term bt times e to the negative 3t, t times e to the negative 3t is in here. So to get around that, our final guess is going to be t squared times that. fundamental set of solutions here also totally overlaps. So our final guess is going to be t times that. So we have t times a e to the 3t cosine of 4t plus b e to the 3t sine of 4t. And for our last one, our fundamental set of solutions is e to the 4t and 1. And so sort of note our initial guess would be at plus b, and then let's say plus c cosine of t plus d sine of t. But we can sort of treat these as separate things. So we have a problem here with b, that is sort of contained, right? It's a constant. So to get around that, we're just going to multiply these first two because those correspond to sort of that thing. So t a to the t plus b plus c cosine of t plus d sine of t. So when you're sort of dealing with these and deciding when to multiply by t, in general, if you have two different terms over here, you can just treat them totally individually and go from there. All right, I am going to stop it there.